First, I'd like to introduce Markus Schedl. He's a full professor at the Johannes Kepler University in Linz, and he leads the multimedia mining and search group. In addition, he's head of the human-centered AI group at the Linz University of Technology AI Lab. His background is in computer science, but he's also studied international business administration. And his research interests include recommender systems, user modeling, information retrieval, natural language processing, data analysis, and web mining. So he spans lots of areas. Really looking forward to his presentation today. And thank you, Markus. I'll stop sharing and you can share your slides.
Thank you very much for inviting me and introducing me, Rosie. Let's go up here. Second. And, yeah. Perfect. Can you see it? Yep. Perfect. Okay, so I don't have to say much more since you already introduced me very nicely. Just want to say that, well, basically I'd like to showcase some of our research where we use natural language processing for different MIR tasks, and just want to start saying that this research and this talk, of course, wouldn't have possible without the great support of my team. So I established the group 2 years ago, so the Multimedia Mining and Search group and the Human-Centered AI group. And actually I'd like to tell you a little bit about 3 research directions we pursue in this realm of natural language processing for music information retrieval. First one is our lyrics analysis direction. The second one is our analysis of music playlists. And the third one is how we integrate NLP to build music exploration interfaces, in particular, the latest ones, even emotion aware. So let's start with the first topic, NLP and lyrics analysis. So here the goal is that we want to identify differences between genres or between song lyrics of different genres in terms of different characteristics, so computational features, for instance, popularity, length of the lyrics, repetitiveness, and also readability. So the research questions behind are these 2, for instance. So can we observe and describe genre differences in song lyrics with regard to these 2 factors, repetitiveness relating to complexity and readability? And second one is there evidence to support this often heard cliche that lyrics of very popular artists are particularly simple and repetitive? So we base our analysis on our data set LFM1B, so 1 billion music listening events extracted from Last.fm. And we enrich this data set with lyrics that we crawled from Lyric Wiki. So for all the artists in the data set, we fetched the lyrics of up to 20 of the top songs, which actually totaled to about 400,000 lyrics. As computational features, we investigated simple popularity counts, like play counts and listener counts, length as the number of characters and the number of words in the lyrics. And these 2 aspects we particularly focus on, so the repetitiveness and the readability. For the former, we use just a compression ratio. So basically, the compressed size of the lyrics divided by the original size of the lyrics. And for readability, we use this SMOG score, a simple measure of gobbledygook. So as for the first research questions, are the genre differences in song lyrics regarding these 2 aspects, repetitiveness and readability? We investigated these genres, as you can see here, and computed mean and standard deviations of compression rates and the SMOG score. And basically the findings, in short, regarding repetitiveness were that R&B showed the most repetitive lyrics, so the highest compression ratio, which was also quite stable, so low standard deviation compared to others. On the other hand, least repetitive lyrics were found in heavy metal music, so lowest compression ratio. At the same time, this was not very stable, so standard deviation was pretty high. In terms of readability, we identified rap as being the most difficult genre to understand. So actually highest SMOG index, this roughly tells you, well, about how many schooling years you need to understand the text. Yeah, but this was not very consistently, so the standard deviation was rather high. On the other hand, punk and blues were the two genres with the lowest SMOG score, so seemingly the least difficult to understand, and this was quite consistently the case. The second research question, so we investigated whether we found evidence that lyrics of the most popular artists are particularly simple and repetitive, and in order to analyze this, we compared those characteristics, so in particular the compression rate and the SMOG index of the lyrics of songs by the top 20 artists with all the other lyrics, so the ones that are less popular. And actually then we performed the t-test to compare the means respectively of the CR and the SMOG scores, and we found that indeed the top 20 artists' lyrics seem to be more repetitive than the other ones, which was, you can see here, statistically significant, but they were not significantly simpler than the other ones. And just to give you some anecdotal examples here, the top performers, so to say, in terms of repetitiveness, so the best compressible lyrics were found in around the world by Daft Punk. It was pretty repetitive, obviously. The easiest to comprehend was Woo Boost by Roscoe. I don't know the song, I have to admit. So with a SMOG score of just 3, yeah, you immediately see. And now the winner in terms of least comprehensible or lowest readability was actually that guy here. If anyone knows that song, Biotics by Devolved, Defense for Sake Logic. Yeah, you see it. It's basically just a concatenation of words, probably without, well, too much meaning. So I also like to showcase you a little bit of our ongoing work. And actually, one is, or some comment we often received is that it would also be interesting, of course, to look at the temporal evolution of song lyrics, not only in particular genres, but also how certain characteristics of song lyrics change over time. And to investigate such aspects, we assembled lyrics from roughly 3 million songs from Genius, and extracted again different kinds of features, again compression rate, readability score, but we are also particularly interested in emotion features, so how positive or negative certain lyrics are and whether this changed over time. We looked into lexical features like repeated lines or how many commas are there. We looked at structural features, so for instance, the number of individual sections, how many chorus sections, and so on. And we also looked at rhyme features. And as I said, this is work in progress, so I can just show you some very preliminary results, so to say. So we investigated this evolution of the different features over the past decades, starting from 1990, and investigated this again for different genres. And what we found, for instance, here regarding emotions is that pop lyrics tended to become less joyful over time. So this NRC effect intensity for joy declined over time. And so did the positiveness for instance, here R&B lyrics. This was even a stronger decline. We also investigated repetitiveness, and in particular here we found notable changes, in particular for rap and pop lyrics, as you can see here. So the repetitiveness here measured as the number of repeated lines in song lyrics, increased quite considerably to a little bit less an extent. This was also shown for pop lyrics. So, second topic is our use of natural language processing for music playlist analysis. This work has foremost been carried out by Harald Schweiger. It's actually one of my PhD students. The basic idea here, or the basic goal, is that we want to identify patterns in music playlists regarding audio features and different kinds of metadata that we investigate. The research questions behind this is, does the track sequence in user-generated playlists matters? So is it, or is coherence of playlists important, so to say? And the second one that we're currently looking at is, are the differences in these coherence requirements or characteristics, are these different for different kinds or types of playlists, depending on, for instance, user intents or activities for which a playlist has been generated? So the data set here, we use the, well, hopefully well-known Million Playlist data set released by Spotify, and which we used for the ASM Recommender Systems Challenge in 2018. And from this, we extracted a subset of around 700,000 playlists that were created by US Spotify users over the time range of 7 years. For features, we analyzed metadata, genre, artist, popularity, which we enriched with, well, these typical Spotify audio features. Well, you all know them, I guess, loudness, energy, and this more or less fancy things like danceability, acousticness, speechiness, and so on. To answer the first research question, so does track sequence in user-generated playlists matters? Actually, let's consider that playlist in here, checks playlist. And actually the question boils down to the question of whether adjacent songs in playlists are more similar than further away tracks in the playlist. And in order to formalize this, we actually defined two different measures here. So the first one is called playlist variance, and the second one is called sequential variance. So the idea is that, well, sequential variance can be regarded as the average distance between subsequent tracks in a playlist, and the playlist distance can be considered as the average distance between arbitrarily, so randomly chosen tracks in a playlist. And we can now actually relate the two, of course, so we can compute the so-called proportional variance by just dividing the playlist variance by the sequential variance. And this, of course, gives us an indication about whether adjacent tracks are more similar than randomly chosen tracks in the playlist. Okay, so we can just subtract one, of course, and then we'll tell you approximately the extent to which subsequent tracks are more similar than randomly chosen pairs of tracks in the playlist. And we found some interesting things, some interesting effects. So actually, not too surprisingly, genre and artist information matters quite a lot. So adjacent tracks in the playlist are commonly from the same genre, also often from the same artist, but also other aspects are important, like loudness, energy, danceability, and so on. So if you want to know more about this, you can have a look at the, well, actually our ISME paper, or maybe you've seen it already, I hope so. It was already presented by Harald earlier at ISME. So what was interesting to see is that the actual differences, so these proportional variances, were statistically significant, but the effect was not very large, as you can see. It was just 15% more, or sequential track were 15% more similar than just randomly chosen track, even for genre and artists, so some things that you would pretty much expect. So we thought of, well, why could this, what could be the reason for that? And our assumption was that coherence is likely not equally important for different types of playlists. So playlists, of course, have different, or creators of playlists have different intentions in mind. Playlists have been created for different purposes, for different activities, and so on. So the next question was, can we identify differences in such coherence characteristics between different types of playlists? And for this, to answer this, and this is what we're currently researching, is that we want to identify clusters of playlists that we identify using playlist embeddings, and we try to explain these clusters or to interpret these clusters using these proportional variance values of these different attributes. And we furthermore also leverage playlist titles in order to try to describe the clusters. So the dataset also contains titles of, well, all the playlists in the million playlist dataset. So in order to create playlist embeddings, we first create track embeddings. So we consider a word2vec model where each playlist is treated as a sentence and each track is treated as a word. And then we create a 50-dimensional embedding for each track. And then we compute playlist embeddings just by averaging all the track embeddings in a playlist. So we end up with a 50-dimensional representation, 50-dimensional embedding for each playlist. We then cluster the playlists. So for instance, here just computing a PCA on this word2vec embeddings. And we can then use actually these different playlist characteristics in terms of Spotify features and metadata in order to try to explain the individual clusters. You see here that, for instance, this blue cluster in here is much more consistent in terms of loudness, whereas this lime cluster is pretty much mixed. So there's a much lower density here and much higher variance in the respective loudness feature. Another thing we're currently looking at is we try to extract information from playlists in order to describe those clusters that we identified through this playlist embeddings. So we use a pretty straightforward, it's just preliminary work, so we use a pretty straightforward approach for now. We just tokenize the playlist titles, we conduct some stopping, some lemmatization, and then we actually model as a bag of words representation all the playlist titles that make up a cluster. So we create another clustering using k-means algorithm. And then for all the clusters, we kind of compute TF-IDF scores for all the words in bag of words representation. Then we just select the words with the highest TF-IDF score in order to describe or to serve as descriptors for the playlist. And this is actually some results here. So for instance, for the loudness characteristics or coherence in loudness, we see that these different clusters have, of course, different PV values. So the highest ones are seemingly the cluster with the highest coherence in terms of loudness, can be or includes a lot of Disney soundtracks, Broadway shows, musicals, and K-pop as well. And this is much more coherent in terms of loudness than, for instance, here, seemingly hip-hop, rap cluster, and so on. But of course, as I said, this is just a rather preliminary thing, so we will invest much more and go much deeper into that. But just to tell you what we are currently working on, so you get a little bit more than just what you got or what you learned when visiting the ISME poster. I hope some of you did. So, and finally, the third topic I'd like to talk about is the use of natural language processing in our music exploration interfaces. So unfortunately, I don't have the time to tell you about all the music exploration interfaces we developed so far. There are quite a few of them. We developed some that are focused on data analysis, and some of them focused on making the music exploration experience more joyful. And I think for this talk, the second category here is more interesting. So we're going to skip the music tweet map and the music tastalizer. So you will find the PDF of the slides. So if you're interested in that, you can have a look later on. And we'll go to the Neptune interface, which is actually an interface that allows users to explore music collections in a joyful way, pretty much like in a computer game, like in a flight simulator, for instance. So what's the approach we adopt? We extract audio features like MFCCs, block level features, and so on from songs in a given music collection. We then create a clustering, so a self-organizing map based on the features. We compute the density of the data points in each of the clusters and smooth the respective densities in order to create a height map where approximately the number of pieces, as that's smoothed, correspond to the height. And then color coded, so we apply a color map. And then finally, we visualize the resulting clustering in an artificial landscape. Use the self-organizing map, just here in 2D. We create a histogram, we interpolate it, and then apply a color map, and then the output is something like that. So this is basically an island landscape where the density is visualized. Data items density is visualized in terms of the height, and the color map supplied that looks like, you know, islands and mountains and so on. Yeah, we also offer different exploration modes, so without showing anything, showing artists and songs, showing descriptive terms, which we extract from web pages, and showing images as well. Yeah, we can also create playlists by just choosing a start track and an end track, and then automatically create a playlist. And this next, just like to show a short video how this could look and sound like such an interaction. Obviously. Good, and finally, I'd like to end up with our most recent interface, which is the Music Tower Blocks interface. Because a problem or a shortcoming of the Neptune interface was that we needed access to the local music collection, so we needed access to the audio, of course, which is kind of, yeah, a bit anachronistic, maybe even nowadays in the area of streaming services. So Music Tower Blocks actually an interface that resolve this and enables user to explore what we call here streaming-sized music collection, again in a joyful way, of course. So of course we don't have access to the audio files, so again we resort to the Spotify audio features and extract them from the top 500,000 songs in our LFM2B dataset. So we used audio features on the one hand, and we also used genre music style features, which we also extract from Last.fm tags and index them using a pretty large list of music genres and styles, again, computing TF-IDF weights. And then in order to create a feature vector for each song, we just concatenate the audio features and the genre features and compute the TSNE projection to two dimensions, sorry, in order to cluster and visualize the resulting tracks. So Music Tower Blocks interface adopts the metaphor of a city that you can explore, that you can walk through. And it does so by representing each song as a block or as a cube, and songs that are nearby in our two-dimensional TSNE projection are stacked on top of each other and form buildings. So nearby buildings then form neighborhoods and so on. So each block is further color-coded in order to indicate its genre. And the user can then, of course, navigate the visualization, as you will see in a couple of seconds. So this was the first version of the interface, so pretty nerdy, pretty computer science-like, I would say. You could highlight, of course, the different genres, for instance. It gets even more cluttered, as you can see here. So it was really more, well, data analysis tool, so to say, but this changed because we actually were awarded a grant for a small project in order to make this suitable for presentation at the Media Arts Festival, so the Ars Electronica Festival, which is an annual festival taking place in Linz. And we created MOMTB, so Emotion Aware Music Tower Blocks, that added an additional emotion perspective, so to say. So it extended the interface I just shown you by emotions that we extracted from tags and integrated them into the interface. So the idea is that for each track we assigned an emotion out of these 4 basic emotions: happy, sad, angry, and fearful. And the user could then select an emotion and received recommendations that are tailored to his or her emotion, and also the visualization, for instance, the weather changed accordingly. So if you're interested in that, you can watch the full explanation video that we made, so a teaser video for the project, and we'll also play you a short snippet at the very end. As I said, we presented this project at the festival, and it was very, very well received. So probably closest to natural language processing, of course, is the question how we predicted emotions for songs, for each song in the collections of this roughly 500,000 songs. So we extracted the emotions from last.fm tags and also from tweets, but that's a different story. We'll not focus on that here. But we adopted a lexicon-based approach, so using a dimensional emotion model. So we mapped words to emotion values according to valence, arousal, and dominance values. So we used 2 dictionaries, ANU and NRC. And the problem was that, of course, a lot of tags were not found in ANU or NRC lexicons. So actually, what we had to do, or our solution for this problem, was that we used another word embedding. And for each target word, so for each tag, we actually computed the word embedding and identified in the word embedding those 3 terms that that were found in the lexicon and that were most similar in terms of the embedding embedding space. And we used bag of words representation using expo. So actually, this means each song was then represented by VRD vectors that we then eventually used to train or we used a pre-trained multi-layer perception in order to predict the song's emotions as a classification task. So classifying each song into happy, sad, anger, or fearful. And actually, this is what the user could use. So the visitors, they could select the feeling. So they were asked how you're feeling. They would receive recommendations indicating also the emotions predicted from the song's tags. And they could then interact with this large city, as you can see here. So this was actually the happy mode. This was the angry mode. So you see when the user changed their emotion, also the weather situation of the interface changed. This was fearful, and there was some fog coming up. Yeah, and finally, I'd like to end here with actually a short part of the video, of the teaser video. Now let's see what my colleague Emilia has to say about that.
The user can stay in his her area of comfort, like let's say his or her. The user can stay in his her area of comfort, like let's say his or her neighborhood, and listen to music the user likes normally, but can also go further away and explore new areas, new musical styles which are not close to the one the user normally likes.
To leave your comfort zone.
Yeah, to leave your comfort zone, and I think this marks a very nice end of the presentation here. Thank you very much.